So in this video, we're going to talk about photon lifetime. So why do we care about photon lifetime? Well, this is going to tell us the dynamics of a laser cavity. It's also going to tell us the steady state operation because we're basically trying to formulate a differential equation in terms of the number of photons in the cavity. And this will, if we solve this differential equation, we can figure out the total number of photons in the cavity. So previously we argued that that should be infinity, but we know in reality that's not going to be the case. So the photon lifetime gives us the first part of this differential equation in terms of the number of photons inside a cavity. So we're trying to figure out what is the rate of change of photons inside some cavity per unit time. So some cavity with some gain, some refractive index. And the photon lifetime is something that basically describes the leakage rate. So how many photons are able to escape this cavity per unit time. And that's what we're going to figure out in this video. So let's say we've got a laser cavity. So we've got some fabry-perot cavity, and it's just this block of semiconductor with some gain and some refractive index. And it's going to have two mirrors on the side. Whether we want them there or not, they're going to be either caused by the interface or introduced by us intentionally. And these mirrors have a certain reflectivity, R. And previously we've been working with the amplitude reflection coefficient because we've been working with electric fields. But now that we're working with the number of photons, which is proportional to the intensity, we care about the reflectivity, not the amplitude reflection coefficient. So we know we're going to have a certain number of photons inside this cavity. So I don't know, maybe we've got 5. And let's call that the number of photons, NP. Now, I'm interested in the rate of change of the number of photons per unit time. And to figure this out, we're just going to use a difference equation. So rather than trying to figure out some continuous derivative, we're going to just figure out what the difference is in the photon count after some time, and then try and work our way back to an actual derivative. And so thinking about this sort of semi-classically, we can think of these photons as individual particles moving with a certain speed. So let's just denote that by they're all kind of moving at the same speed. Maybe some are moving to the left and some are moving to the right. We don't really know. And the speed of these photons is the group velocity. So the number of photons is proportional to the intensity of light. And the intensity or power or energy in general propagates with a group velocity rather than the typical phase velocity that we use. So it's not just c over the refractive index, but it's c over the group refractive index, which ideally is the same, but not always. And so we want to figure out for a given delta t, what is the change in photons delta n? And so first we have to choose a delta t, and really we could choose any delta t. We could choose the time it takes photons to go this distance, delta L, or maybe this distance, or really any distance that we want. But a somewhat natural distance is the round trip time. So if we use the round trip time, so in other words, I've got this photon right here, bounces first off this mirror, goes all the way back here, and then all the way back here, then that's sort of nice because all the photons retain their initial positions. So after the round trip time, this photon comes back here, this photon comes back to this position, and so on and so on. And we're also going to assume right now that there's no gain. So we've turned off the gain and we just want to see what happens to the photons that are remaining in the cavity. So conceptually, I find it a little easier rather than working with a bunch of different photons moving in a bunch of different directions. I find it conceptually easier to work with just, let's say, a wave front of photons or a bunch of photons all right next to each other, all moving in the same direction. So let's say we have 10. Let's make a total of 10 photons. And they're all moving to the left initially with a certain group velocity. Then after some time, they're going to travel all the way to this new mirror, or to this mirror on the very left-hand side. So they've now traveled right next to the mirror. And a certain number of them, when they bounce off of the mirror, when they interact with the mirror, a certain number of them are going to escape. And that's given by the reflectivity. So if R, for example, was 0.3, then we'd have 3 of these photons returning back into the cavity. So 3 of these photons returning back into the cavity, and 7 photons escaping. And let's actually draw out 7 arrows. So we've got 7 photons escaping and 3 coming back into the cavity. Or if NP is our number of photons, we have R times NP returning into the cavity, and 1 minus R times NP photons escaping. And so the photons that are remaining, well, they're going to go all the way back to this right-hand mirror. And if you're wondering why they're just traveling in these directions, why they're just traveling in the X direction, let's say, that's because these photons were all stimulated photons. So they're all part of some coherent mode that's only moving in this lateral direction, or only a sine wave, essentially, that's only supported in this X direction. But anyway, let's say that these photons move and they travel to this new mirror. And let's say this mirror has the same reflectivity, so for example 0.3. Then now we've got 3 photons and we need to take 0.3 of that, and that's kind of awkward. But approximately 2 of the photons now are going to escape and 1 is going to return. But in reality, we're going to have something like 30 quadrillion photons. And so you can actually take a fraction like this of a massive number of photons. But actually, why don't we just say that it's equal to 0.33 repeating, so that there's no conceptual difficulty? So this is going to be R2 and this is going to be R1. So the mirrors are going to have different reflectivity. So 2 of the photons are going to leave and 1 of the photons is going to get reflected. And then this photon is going to take a certain time to get back to its initial position, and then it's completed 1 round trip, which took a certain time, delta t. And we've also lost a certain number of photons. So now what is that round trip time, delta t, and what is the change in the number of photons, delta n? Well, delta t is very simple, or fairly simple, because we know that the total length the photon has traveled. So this is it traveled 1 entire length of this cavity, and then back again. So the total length that it traveled was 2 times the length of the cavity. And its velocity, we just said, was the group velocity. So this is the total time that it takes a photon to make a round trip. And now what's the change in the number of photons? Well, this is just our photon count, our initial photon count, minus our final photon count. And so our final photon count, initially we had R1 times NP, and now after reflection, we're going to have the photons that we initially had to hit the mirror times R2 times NP. So delta n is just going to be our initial number of photons minus NP times R1, R2. Or if we factor that, it's just NP times 1 minus R1, R2. And really, I probably should have written this as final minus initial, because we want to know the sign tells us that we've lost photons. So I'm going to slap a negative sign out front here to indicate that delta n is negative. We are losing photons to the outside world when we do this. So now we can formulate our difference equation, delta np delta t. This is just now np times 1 minus r1 r2 divided by the round trip time, which we just said was 2 times the length of the cavity divided by the group velocity. And I'm just going to say that this is equal to the derivative. So this is equal to the derivative of the number of photons leaving per unit time. This should have a negative sign out front. And why is it equal to the derivative? Well, in reality, we don't have a phase or a wave front of photons. We've got photons interspersed all throughout this cavity. So we're not losing a large number of photons at once and then losing another large number. We're sort of losing one photon and then another photon, then another photon, then another photon. And if you have enough photons, and we're going to have like a huge number of photons, like, I don't know, 10 to the some large number that's greater than 10, then this staircase will start to really, really look like a curve. And so we can really just interpret our difference equation as the derivative. And if we want to write this more succinctly, we know that this constant here, this thing that's multiplying NP, has to have units of 1 over time, because we've got a 1 over time in this denominator. So we can write that the total number of photons change per unit time is just negative the initial number of photons divided by this constant. Let's call it tau p. So tau p is just, by definition, equal to 2L over Vg times 1 minus R1 R2. And this is the photon lifetime. Photon lifetime. So if we've got a certain number of photons within the cavity and we had a certain gain and then we turn it off, so we turn off the gain, the photon count will decay according to this differential equation. And we know the solution to this differential equation. This is just a decaying exponential. So the number of photons decays like e to the minus t over tau p if we turn off the gain. So in the next video, we're going to be turning back on the gain, and we're going to be completing this photon rate equation so that we can figure out how many photons are inside the cavity. So I hope you enjoyed the video. If you did, please give it a like below and subscribe to my channel. Also, if you have any questions or comments, please post those down below and I'll try to get back to you as soon as I can. And thanks for watching. I'll see you next time.